Welcome to an introduction to autonomous systems of ordinary differential equations and vector fields. A system where the equations do not depend on the independent variable is called an autonomous system. For example, the system y prime equals 2y minus x and y prime equals x is autonomous as t is the independent variable but does not appear in the equations. For autonomous systems, we can draw the so-called direction field or vector field, which is a plot similar to a slope field, but instead of giving a slope at each point, we give a direction and magnitude as a vector. The previous example, x prime equals 2y minus x and y prime equals x, says that at the point x comma y, the direction in which we should travel to satisfy the equations should be in the direction of the vector where the x component is 2y minus x and the y component is x. Notice how the x component is x prime and the y component is y prime, where the speed is equal to the magnitude of the vector. So we draw the vector 2y minus x comma x at the point x comma y, and we do this for many points on the xy plane. For example, at the point 1 comma 2, we draw the vector where the x component is 2 times 2 minus 1, and the y component is 1, giving us the vector 3 comma 1, which is a vector pointing right and a little bit up. Well, at the point 2 comma 1, we draw the vector where the x component is 2 times 1 minus 2, and the y component is 2, which is the vector 0 comma 2, a vector pointing straight up. When drawing the vectors, we will scale down the size to fit many of them on the same direction field. If we draw the arrows or vectors at the actual size, the diagram would be a jumbled mess once we draw more than a couple arrows or vectors. So we scale them so that not even the longest one interferes with the others. We are mostly interested in the direction and relative size. Here's an example. This is the direction field for, again, the system x prime equals 2y minus x and y prime equals x. Notice all the vectors have been scaled, so they fit nicely on the graph. We can draw a path of the solution in the plane. Suppose the solution is given by x equals f of t and y equals g of t. We pick an interval of t, say the closed interval from 0 to 2, and plot all the points f of t comma g of t for t in the selected range. The resulting picture is called the phase portrait or phase plane portrait. The particular curve obtained is called the trajectory or solution curve. So below the entire graph is a phase portrait or phase plane portrait, and the red graph is a trajectory or solution curve. In the figure, the solution starts at the point 1 comma 0 and travels along the vector field for a distance of 2 units of t. We solved this system precisely in the last lesson. I've included the solution below, so we can compute x of 2 and y of 2. X of 2 is approximately 2.475, and y of 2 is approximately 2.457. This point corresponds to the top right end of the plotted solution curve in the figure, which is this point here. Before we go, there's a lot of software out there that can graph phase portraits. Let's take a look at one free online option. This page plots a system of differential equations of the form dx dt equals f of x comma y and dy dt equals g of x comma y. By default, we have x prime equals y minus 0.5x and y prime equals sine x. Below, we can change the display, we can change the window, we can change the arrow length, we can change the number of arrows. We can also click on this box here for variable length arrows. Let's leave the default settings and click Graph Phase Plane. Notice now below we have a nice phase portrait where all the vectors have the same length. If we want variable length vectors, we click the variable length box and click Graph again. If we don't want these overlapping arrows, we can change the arrow length. For example, if we change 15 to 10, it will scale all the vectors appropriately, and we can adjust the vector length as needed. We can also click on a point on the phase portrait, and it will graph the trajectory or solution curve passing through the given point. And we can do this multiple times. I hope you found this introduction helpful.